Okay, ladies and gentlemen, let us resume with part 2 of the lecture. In this part, we'll start the discrete time Fourier series. Up until now, we have been talking about the continuous time Fourier series. So, the title is Introduction to Discrete Time Fourier series. Okay, now there are many similarities and a couple of dissimilarities between the continuous time Fourier series, that is the CTFS, and the discrete time Fourier series, DTFS. First of all, we have said that Fourier series works for, or rather I should say, Fourier series is applicable, not applicable, is useful in the case of periodic signal, either continuous or discrete. So continuous time Fourier series is, we have seen that works with the continuous signal where the value doesn't essentially occur as various samples. The discrete time Fourier series is used for the Fourier analysis for the discrete time periodic functions. Now, throughout the derivation, we shall be assuming the discrete periodic signal, which is x of n, which will be having a period of n. Similarly, as for the continuous time Fourier series, our target will be to expand x of n as a running sum of some weighted sinusoids with various harmonics. What I mean by that is we are required to expand x of n as a number of sinusoidal signals having various frequency components. Like CTFS, we can write the expression for DTFS to be x of n, which works as a running sum of k, which goes from 0 to n minus 1, c of k, which is the discrete time Fourier series coefficient, and e to the power j of twice pi kn over n. Now let us compare it with the CTFS expression, which is x of t, that is a running sum over k, which goes from minus infinity to infinity, c of n, e to the power j twice pi f naught k t. Now here in both the equations 1 and 2, f naught over here, f naught is analogous to 1 over n, which is the time period, that is this part, and t, which is the continuous variable of CTFS, here will be n, which is discrete in nature, and n is always integer. We get the fundamental period of DTFS to be capital omega naught, or we can represent it with small omega naught, equal to twice pi over n, n being the discrete time period. Now, what about the limit? the limit of CTFS goes from minus infinity to infinity, but upon closer inspection we see the limit of DTFS goes from 0 to n minus 1. Why is that so? Because since I have said that x of n is a periodic signal with a period of n, and if we calculate from minus infinity to infinity, it will work, it will obviously work, but doing so the terms become redundant. That means from 0 to n minus 1, if we calculate the running sum from 0 to n minus 1, the value will again repeat for n minus 1 to then n will be the value of k equals 0, and similarly n plus 1 will be the value of k plus 1. Let me explain it mathematically. Closely observe this term over here. If the signal is periodic, e to the power j 2 pi kn over n must be equal to e to the power j twice pi k of n plus n to the n plus n times n over n. That means it is the condition of periodicity. If a function f of x is periodic, then the value of f of x will also be equal to f of x plus n, where n is the time period. Let us explain. If this is a sinusoidal function f of x, so the value, the time period up to here is n, and f of x plus n, that means this part will be having the same value as f of x. I mean x plus n in the x-axis will have the same value as x. So if we can prove that these two expressions are equal, so we can say that, from that we can say eventually that the limit need not to be from minus infinity to infinity, rather it can be taken from 0 to n minus 1. So let us show mathematically how it works. First of all, we consider this term to be e to the power j n plus k omega naught n. Now expanding this, e to the power j n omega naught n, obviously omega naught equals twice pi over n, and e to the power j omega naught k of n, and the next line becomes j k omega naught n e to the power j, we can write omega naught as twice pi over n and kn. I have written this term over here and this term over here for your clarification, and n and the small n. So cancelling these two terms, the expression becomes e to the power j k omega naught n e to the power j twice pi k n. I'm afraid, sorry, let me rewrite this equation. It becomes, from this line, e to the power jn, this becomes jn, omega naught becomes twice pi over n, n remains as it is. This term we shall not change, omega naught k of n. Cancelling this two term, we get e to the power j twice pi n. And for any value of n, we see that this term will always be 1. This is shown in the previous lecture, where in the problem I've shown that e to the power minus j n 2 pi for any value of n will become 1. So if this value becomes 1 and the remainder remains, the remaining expression remains as it is, j of omega naught k of n, we get e to the power j n plus k pi naught n or omega naught n equals to be e to the power j omega naught k of n. So from this expression we see that k plus n will have the same value as of k. That means the signal will be repeating itself after each period. So the range of frequency for the continuous time, which has been minus infinity to infinity, is redundant in this case of DTFS, from where we can take from k equals 0 to n minus 1. Now then, the limit 0 to n minus 1 means that there are how many number of samples? N naught. I mean n samples. 0 being the first sample, 1 being the second sample, 2 being the third sample, and 3 being the fourth sample, and so. So n minus 1. Otherwise, we can also take the limit, I mean the summation limit, which was k, which goes from 0 to n minus 1, to be k equals 1 to n. And this will yield the same value as k equals 2 to n plus 1, and so on and so forth. But in our calculation, we will be considering this value. Hope this is clear that why the limit changes from the continuous time Fourier series to the discrete time Fourier series. Okay, now let us go to the derivation of the Fourier series coefficients. Discrete time Fourier series coefficient, where we get the expression to be x of n, where n goes from k equals 0 to n minus 1, c of k, which is the discrete time Fourier series coefficient, e to the power j n k omega naught, and of course omega naught equals twice pi over n. Now in order to calculate the value of c of k, first of all we must multiply both sides of this expression. Let us mark it as a with the, let us multiply both sides of equation a with e to the power minus j l omega naught n. So the expression becomes x of n e to the power minus j l omega naught n, where L is quite analogous to k and is an integer, and the right hand side becomes summation of k goes from 0 to n minus 1, and c of k e to the power j n k omega naught e to the power minus j l n omega naught. Now the next step will be to take a running summation of n, which goes from 0 to n minus 1 in both sides. So this becomes x of n e to the power minus j l omega naught n, and the right hand side consequently becomes n equals 0 to n minus 1 summation of k, which goes from 0 to n minus 1. I'm writing this summation: c of k e to the power j n k omega naught and e to the power minus j l n omega naught. Let us mark it as equation B. Now, considering the right hand side of equation B, we get, as per the property of running sum, we can interchange these two values. So if I take this value before this one, I mean this summation of operator before this one, the value wouldn't change. So let me write it down. K goes from 0 to n minus 1. C of k, which doesn't depend on the value of n, can go outside as well. But C of k must remain inside this summation, as C of k depends on the value of k. So n equals 0 to n minus 1. The remainder of the experiment, I'm sorry for the stuttering, the remaining part remains as it is. K minus L n omega naught. Now what about k minus L? These two are two natural logarithm multiplied, so the exponents can be subtracted. So let me write this down as n naught n minus 1 c of k, and this whole expression, let me mark it, this part I am considering it to be w of a. So let me write it down as w of a. Now again, we must come to two assumptions. By two assumptions, I mean that two cases where in case 1 we shall consider k to be equal to L. Now if k equals L, w of a becomes summation of n, which goes from 0 to n minus 1 e to the power j of k minus L and omega naught. And now if k and L are equal, we can write n equals 0 to n minus 1 e to the power j k minus k and omega naught. This in turn dictates that n goes from 0 to n minus 1 e to the power, since this value is 0, the entire term becomes 0, so e of 0, which in turns become n, which goes from 0 to n minus 1, and e to the power 0 is 1. Now, what are we doing here? We are doing that we are actually summing the value of 1 from 0 to n minus 1. So what will be the result of this expression? Okay, before going to that, let me recapitulate what we have considered earlier. We have seen that 0 to n minus 1 will have n number of samples. Likewise, k from 1 to n will also have n number of samples, and k from 2 to n plus 1 will have n number of samples. So essentially what we are doing is summing 1 up to n times. So this can be written as 1 plus 1 plus 1 plus 1 plus dot 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 dot. It's 1. This is the nth time. So adding n number of ones will result in an value of n. So omega a, I mean WA in this case becomes n.